Over the years, I have had many questions about power sensors. It's dated back a couple of years ago. And people want to know how to build their own power sensor. What is a power sensor? Can you repair a power sensor? Why are the power sensors more expensive than the actual box they plug into? A whole bunch of questions along those lines. And so I went onto eBay and I bought a dead sensor. So these things are very fragile and they're very easy to destroy. And this one's been blown up. I plugged it onto my machine, and even though it can recognize the sensor, there's no voltage coming out of the front, so it fails calibration. It's interesting, this one looks like it was part of Qualcomm. It says failed calibration. This says Kyocera calibration seal. There's a asset tag on it. Yeah. So this is a Gigatronics power sensor. So this is after they purchased the WaveTech microwave group, but WaveTech had this particular sensor a long time before that. This one's good up to 18 gigahertz. All right, so before we tear this apart and I show you what's going on, let's talk about what a power sensor looks like. All right, so here we have a sensor. It has some type of connector here. In our particular case, we have an N connector on the front. And it goes into a 50 ohm resistor. So power sensors always detect the amount of power something can deliver into 50 ohms, okay? You can get probably sensors that are calibrated to 75 ohms in other systems, but most of them are going to be calibrated to a 50 ohm system. So what are you going to measure here? Well, you're going to have some voltage here, right? And you can measure that voltage, and now you have a power meter. That's all there is how many volts across a 50 ohm resistor tells you how much power there is, right? So it's V squared over R. And I've done this on other videos. I've shown you what if you don't have a power meter. If the frequency is low enough, let's say I have a 350 megahertz oscilloscope, okay? So I could measure this. I could measure the RMS. You want to make sure you measure the RMS voltages. I can measure the RMS voltage of the signal with my 350 megahertz oscilloscope, and I have a power sensor up to 350 megahertz, okay? So however fast your oscilloscope is, you can go up. Now, using a voltmeter is going to be a bit dodgy because most voltmeters won't even go up to a megahertz for AC signals. So you're really kind of stuck with using a oscilloscope. So this is the basics of what you want to do. Well, what if you don't have the ability to measure it? Let's say it's a 1 gigahertz signal, and your oscilloscope isn't good to a gigahertz. Well, you could try to build your own circuit, okay? And so you could start out with the 50 ohms. You always need the 50 ohms. And you could say, I'm going to build my own circuit. Let's see here. I'm skipping ahead. So let's forget this for now. So in the past, let's go back in history. In the past, there were other ways of measuring instead of measuring voltages. You could look at the heating of this resistor, okay? The temperature or the delta temperature of that resistor. You could measure its temperature without a signal, and then you could put a signal into it, wait a while, and you can measure the temperature rise of this resistor, and you could calibrate that system, and you could measure watts by how many thermal watts do you have. How many thermal watts, you'd have some mathematics that converted that thermal watts into RF watts, okay? So that would be something like a bolometer. You might see that, bolometer. And a bolometer basically measures the heat in the system. It's usually in a bridge circuit, and you have one resistor that is in the RF path and one other resistor that's not, and you look at the two, and then when you introduce this, there'll be an imbalance because one heats up, and you can calibrate that all. So that's the way it was done probably in the 1910 to 1950s kind of region. And And then they went to a system that was thermistor based, okay? So now you're going to also have a 50 ohm resistor, but you're going to measure the change in resistance due to the RF coming in. So the RF will heat up the resistor and its resistance will change. And you can put that in a circuit and you can measure that resistance change. So that's a thermistor based. And you could look at differences. You could think of it as differences in temperature, differences in current, differences in voltage, whatever. You're using this thermistor, which is a particular type of resistor that's going to change voltage with temperature. It's still a temperature effect, but you're going to be measuring DC voltage after that. So anyway, that's how a lot of power sensors were built up to around 1970, something like that. And then comes a different type of sensor. Okay, so let's talk about different type of sensor. All right, so this one again, we're going to have a 50 ohms. All right, and then we're going to say, okay, well, let's rectify that. We know there's a voltage here that we're interested in, an AC voltage that we're interested in. Okay, let's rectify that. And we'll change that into some type of DC voltage, and then we can just put a DC voltmeter over here and we can measure it. Okay, so this is a diode detector. And I don't have one, but it's very, very common to see something that looks just like this that says detector on it, okay? And what it is it's one of these. It's just a diode and a capacitor inside of a little package like this. And oftentimes you'll use something like this to monitor the amplitude of a particular signal. You could put it in a feedback path and stabilize the power output of a device. You could put it into a kind of a path where you use it for leveling, like a spectrum analyzer. If you have some type of RF signal that's changing, the power will change with frequency, and you need to monitor that and then use that as a feedback to level things. So before digital equipment where you could just hit normalize, you'd have to measure it, sample it somehow. So sampling circuit here. All right, but this is what's in here, okay? It's going to be fancier than this, but this is basically the idea. We are going to have a diode and a capacitor, and then we will measure DC volts, and that's all there is to it. Now, these little guys will only tolerate so much power, so they're quite sensitive to blowing up if you hook a wrong amount of power up to it. This one says it's good to plus 23 dBm, peak or average. And so, yeah, it's pretty easy to destroy these things. So, let's see here. Do we want to go farther with the explanations, or we should dig into it? I think let's dig into it, and then once you see it, you can then appreciate what this is. Now, one thing I'll say right from the get-go is this is not a linear system, so it needs to be calibrated. So if you plotted, let's see, if you plotted watts in, that's going to go in here, and volts out, okay, it's not going to follow a straight line. It might even be lumpy. I mean, it could be anything, right? But it's definitely going to have a curve. It's going to have a curve to it. These things are not linear. These things will also change with temperature. So it'll go up or it'll go down with temperature. They're not linear with frequency. So if you put in 1 gigahertz, it might be here. If you put in 20 gigahertz, it might be way down here. So they're not linear with gigahertz either. So inside this thing, you'll need to put a thermistor to measure the temperature in here, because you'll have to calibrate this thing over temperature. So if you know the temperature of this, you can add a cal factor. You're also going to need to know what frequency you're going to be operating at, because there's different cal factors. So in the old days for HP sensors, there was a table on the back, and it told you how many how many gigahertz, and it told you what calibration factor it was, and you had to dial that on the front of the instrument, okay? Well, this has all that information in it, but it's in the E² prom. So when you connect the cable to this thing, there's quite a few pins on this cable. It actually reads the E² prom, it knows what type of sensor it is, and then it downloads all the calibration data for this thing. So that's one of the reasons these things are so darn expensive, is because they have to go through a calibration, a lengthy calibration. They're calibrated for power, they're calibrated for frequency, and they're calibrated for temperature. And all that data is stored in the E² prom in here. So, you know, short answer of can you build one of these? Yeah, but you have to have a cal lab to generate all that cal data, okay? And even if you could generate all that cal data, I'm going to show you probably why you can't build one of these anyway. But yeah, let's see if we can't open this thing up and not destroy it too badly. So I have taken it out of the tube here, 2 end caps, and this was what's inside. So first of all, you'll see there's lots of circuitry in here, and we will need to talk about that. Here is the connector. Like I said, has lots and lots of wires, and then the actual detector, okay, is up in this section here. So let me show you that. Move this out of the way. Let's zoom down here. So I'll put this under a different microscope, but basically there is a voltage regulator. This is the E² prom that holds all the calibration data. There's actually 2 voltage regulators, plus and minus, and there's a bunch of circuitry in here. And long story short, this is a chopper stabilized amplifier, okay? And so there's a chopper amplifier right up in the sensor, so as close as you can to the diodes themselves, you want to do the detection. And then there's a little blob of white right there. That's some RTV. There's a thermistor there, so it's measuring the case temperature of the sensor, because you need to know that. Op amp, chopper. Anyway, we'll go through all of that. But there's a spacer here to make it all fit. So I already have loosened this. Let's loosen this. Notice it's gold. That is gold plating. It's gold inside. And we'll talk about that. There's a reason it needs to all be gold. And then this is the end connector here. And there's a little thing here that I can pull out. And there's the detector, okay? This is the thing with the diodes and the capacitors and stuff in it. And this is just a housing for the connectors, okay? So this is the magic here. So if you sent one of these back in and said it doesn't work anymore, they would need to replace this part here and then recalibrate it, okay? And it will probably cost you as much as a new one, I would imagine. And so there's a little C-clip here to take this apart. We'll do that. Let's first take a look at the circuitry. Let's see here. Is this a good lens for it? No, I'm going to take this all into a different room, and we'll use my nice microscope there, and we'll take a look at both of these things in there. Okay, here is the PC board. The detector is over here, inside here, that little pellet thing. And so it comes in this way, and then everything goes out on this multi-pin connector. The multi-pin connector supplies voltages. It supplies clock, I think. It supplies an E² signal. I squared C, I think, goes to the EEPROM, which is right here. So all the cal data is stored in this EEPROM. The signals here come in, and then they go through a bunch of circuitry. And if you think that was complicated enough, yeah, there's a bunch of stuff on the bottom too. So a lot going on. I don't have a schematic for the sensor, so I can't show that to you. But basically, the signals come in here. There'll be a plus signal and a minus signal. I'll talk about that a little bit later. They come into the circuit. There's a FET switch here and a FET switch here. Those allow chopping action. So this is a chopper stabilized amplifier with these two op amps here being the being in the circuit. It's running off a plus or minus 5 volts. So there's a 5 volt regulator and a minus 5 volt regulator. Yeah, so there's a little thermistor here going into this aluminum housing, so it measures the case temperature, keeps track of that. Yeah. Not quite sure what that one is. 74. Might be a flip-flop. Might be this thing needs a flip-flop or a signal up and down, up and down. That might just be a 74 with an 8-pin 74 for 74. I don't know. Maybe there's such a thing. I'll have to look that one up. Yeah. So anyway, there you go. Looks like 2 other flip-flops on the bottom there. Kind of interesting, or whatever those things are. I don't know what those are. Maybe they're not flip-flops. Yeah, strange stuff. Anyway, so you're saying, oh, yeah, there's a lot of stuff there, but I can recreate that. I can lay out PC boards. I could reverse engineer this. I could do all of that. Yeah, but what you can't do is build this detector. So let's take a look at that next. All right, I've taken that little clip off there, and we can slide this over to expose all the RF goodness inside. Yes, there's RF goodness in there. Nothing on the back. This is an alumina substrate, so we're going to have to get closer. All right, that's a pretty good looking picture. So the RF's coming in from the left, and the DC is going out to the right. And so if we start on the pin, there's a pin right here by my finger. So that's the RF coming in, and it will come into a section here, and it will end up on that gold pad right in the center. Okay. Now, if you go from left to right, there will be a. I don't think this is going to just be too hard to point with things. Yeah, it's just too small in there. So I'll have to mark it here on the video. There is a 50 ohm resistor to ground. So that's what goes right through the center there, this 50 ohm resistor. And then there are 2 diodes. And one of them is backwards. So there's one diode that detects positive peaks and one diode that detects negative peaks. So those 2 diodes span between the center pin of your RF connector and a capacitor. So they're bonded to the top of that capacitor. So in this particular sensor, if I had to guess, one of those 2 sensors is dead. And you can see that you might have a hard time repairing this thing. I don't think you can get a good sense of how small those things are, but you can see the bond wires there. Yeah, these things are pretty small. And they're not soldered on. Everything is gold connections. You don't want to have any dissimilar metal connections that cause voltage sources. So yeah, so 2 diodes, one detects positives, one detects negatives. They go onto those 2 squares there that are the capacitors. And then those capacitors then get wire bonded way back to another little just RC circuit just to smooth things out. And you can see here that they have wire bonded the resistors out of the circuit. So there used to be a little RC circuit there, but they decided for this particular sensor design, they didn't want that resistor in there. So they've wire bonded those 2 resistors out. Those resistors are deposited on the alumina substrate. And then 2 voltages go out the back, a positive voltage and a negative voltage. And then ground is the case. So you have 3 signals. You have plus, minus, and ground. And yeah, that is what's inside these detectors. Now, you say, okay, I can work with really, really small things. I'll just buy myself some replacement diodes. Well, you can't. These diodes are not anything you can order. They just aren't. They were special. We had a manufacturer that we worked with who built diodes, and once in a while, for whatever strange reason, by dumb luck, they built perfect diodes. They had really low capacitance, really low junctions. They had great, 40 gigahertz capability and stuff like that. So every once in a while they got lucky, and they would call us on the phone. We would go over, and then we would buy that entire lot. We would buy a wafer of diodes that had this particular characteristics. But you as an individual could never go to that company and say, "Hey, I want some of these." This just wouldn't happen. So just to make it a little easier to understand and recap here, this is what the sensor schematic would look like. There's that 50 ohm load and two diodes, zero bias, Schottky, low barrier, fancy, can't get them diodes, and then two capacitors that allow you to develop plus and minus signals. And the reason for two diodes instead of one diode is you get more signal. And so that's one of the patents, I think, that was on this particular device. Here is a drawing I made before I actually got a sensor in my hand, but I believe the sensors come in different flavors and stuff. And this is what this is what was in my memory from 30 years ago, was that the RF comes in from the right, and there is a transition section of RF transmission line that takes you from a certain radius and frequency and stuff, and it snakes it down to a small size and keeps it all perfectly 50 ohms all the way through. It's actually even more complicated than that. There's an actual patent for these sensors where the layout is such that it adds a little bit of capacitance and adds a little bit of inductance all in the right places to keep this thing operating up to 40 gigahertz. So yeah, it's even more complicated than that. I had a guy who was his entire job, was the device physics of this whole thing. So here's a photograph of an Agilent sensor. This is from a video that was on the channel The Signal Path. And he did a very nice I think he actually has two videos on power sensors and power meters, but he did a nice teardown of this one. This is kind of a more modern sensor from Agilent. I don't know if it's Keysight. I think it's Agilent. And you can see they also have this tapered transition line that comes into there. Now, they don't use individual diodes. They've created their own fancy diode hybrid, I guess you'd call it. And here it is. It has also the plus and minus voltages with dual diodes, but it also has a pad. It has an attenuator inside. So it has two ranges. It has a high range and a low range, both in the sensors. That's how they decided to do it. Yeah, this says Agilent on it. So anyway, yeah, you can see here, it is very complicated. And of course, you'd never be able to fix this one because it is a special part from Agilent. So I'll put a link down below on his video, which is very good. So there you go. That was my introduction to the sensors that I'm familiar with, and why they're hard to build and expensive to build and hard to repair.